Hello there and welcome back to the Science Sleepy Minds. Tonight you're adrift in a black sea pricked with diamonds, distant galaxies, each spinning lazily like cosmic pinwheels. There's a breeze in the void. Not a real breeze, obviously. You're in a vacuum. But something feels off. You rotate ever so slightly, like a compass needle with nowhere to point, and then, curiously, you start to notice. Many of these galaxies around you are spinning in the same direction. Coincidence? Maybe, but also maybe not. You might have just stumbled onto one of the strangest clues the universe has left lying around, that it might actually prefer to spin in one direction over another. You probably won't survive this idea intact. That's because it threatens one of the foundational assumptions of modern cosmology, that the universe doesn't play favourites, that it's directionless, symmetrical. But if galaxies, these enormous spiralling masses of stars and dust, have a spin bias, then that symmetry might be just a comforting myth. So before you get comfortable, take a moment to like the video and subscribe, but only if you genuinely enjoy what I do here. And don't forget to drop your location and local time in the comments. Where in the world are you tuning in from tonight? Now dim the lights, maybe turn on a fan for that soft background hum, and let's ease into tonight's journey together. You drift closer to one galaxy, somewhere between the toes of Andromeda and the elbow of Virgo. It spins clockwise from your perspective, its spiral arms elegantly trailing behind its rotation, like a dancer's swirling skirt. You turn to another, same direction, another, still clockwise, and another, clockwise again. The pattern begins to itch at your brain. In a perfectly random, direction-neutral universe, you'd expect an even mix of clockwise and counterclockwise galaxies, depending on your viewpoint. But astronomers have actually tallied thousands of spiral galaxies, and guess what? The count seems tilted. A study in the early 2000s catalogued over 15,000 spiral galaxies, and the results raised more than a few eyebrows. The southern hemisphere showed a statistically significant preference for one spin direction, while the northern skies leaned the other way. Now, skeptics were quick to jump in, pointing fingers at data biases. Maybe telescopes or image analysis software were unconsciously favouring certain orientations. But the signal didn't quite vanish under scrutiny. In fact, newer machine learning surveys, programmed to be neutral, showed the same trend, just more subtly. Historians still argue whether this is a true feature of the cosmos or simply a trick of the data. After all, humans are great at seeing patterns, even when they're not there. But suppose it is real. Suppose there really is a universal handedness, a twist to space itself that spirals galaxies into submission. That would mean there's an actual physical direction in the universe, like a cosmic up or left. It would violate something called cosmological isotropy, which we'll gently tiptoe into in the next section. For now, you slowly spin yourself in space, trying to imagine what this means. A preferred direction would mess with a lot of neat equations. Physics likes symmetry. Symmetry keeps things clean, predictable, elegant. If the universe prefers left-handed spirals, it's like finding a smudge on a mirror that was supposed to be perfectly polished. And here's the kicker, it's not just spirals. If you squint at the behaviour of other massive structures in space, you might find a similar lean. Quasars, those energetic jet-spraying cores of ancient galaxies, also show suspiciously consistent alignments over huge distances. That's a bit like looking out at an ocean of people and seeing that their shoelaces are all tied the same way. Odd, to say the least. Let's get weirder. There's a concept in physics called parity violation. It basically means the laws of nature aren't always mirror-symmetric. On the quantum scale, particles sometimes behave differently from their mirror image counterparts. But that's tiny scale stuff, down in the realm of atoms and quarks. If this galaxy spin thing is real, then parity violation might be happening on a cosmic scale. That's like seeing the quirks of a microbe replicated in the motions of a whale. Still floating. Good. Now imagine the old school philosophers, Aristotle for instance, who thought the heavens must be perfect and eternal. They believed celestial motion reflected divine symmetry, but even ancient skywatchers might have noticed peculiarities. The Chinese astronomer Shen Kuo, way back in the 11th century, wrote about the rotational motion of the sky and hinted at asymmetries. Of course, he didn't have a redshift catalogue or a radio telescope, just his eyes and a lot of patience. But the idea that the sky isn't perfectly balanced goes back 1,000 years. The modern data, though, has sharper teeth. Some cosmologists now seriously entertain the idea that the universe has a large-scale chirality, a handedness. That would make it a chiral structure, just like a seashell or a snail, not reversible, not symmetric. It would mean that no matter where you are in the universe, if you look far enough, you'll see galaxies curling in one dominant twist, and that's not supposed to happen. One fringe idea, that this spiral bias is a memory, a fossil imprint from before the Big Bang. Maybe our entire universe was born spinning, or birthed from an interaction with another dimension that brushed us in a specific orientation. That's the kind of sentence that could get you side-eyed at a physics conference, or invited to give a TED talk depending on your charisma level. Of course, most mainstream physicists still treat this with caution. The data needs to be cleaner, broader, deeper. We've only been peering into the depths of the universe for a century or so. Our cosmic map is still being filled in, and until we've seen more of the sky with better tools, it's easy to get carried away by noise. But you, floating out here in the quiet dark, can't help noticing the pattern. Galaxy after galaxy, twirling like leaves in the same invisible breeze. It makes you wonder, what if the whole universe is caught in a slow ancient whirlpool? What if there is a great cosmic swirl and we're simply too small to feel it? You close your eyes for a moment, letting the spin pull at your imagination like a gentle tide. Not enough to disorient, just enough to hint. Something is leaning ever so slightly in one direction. And maybe, just maybe, you are too. You open your eyes again just as you drift past a strange glow, faint, ghostly, and omnipresent. It wraps around you like a warm static, the last afterglow of the Big Bang itself. This isn't ordinary light. No, this is the oldest light in the universe, the cosmic microwave background. Or, if you're feeling informal, the CMB. Discovered in 1965 almost by accident, as all the best things are, the CMB is the universe's baby photo. A snapshot taken roughly 380,000 years after the Big Bang, when everything had finally cooled enough for atoms to form and light to travel freely. And while it looks uniform at first glance, a soft speckled beige across the cosmic wallpaper, scientists with ridiculously precise instruments have found it's anything but. You ease closer, letting the pixelated speckles resolve around you. These aren't just pretty colours, they're temperature variations. Tiny ones. We're talking 1 part in 100,000. But within these delicate fluctuations lie secrets about the structure, expansion, and possible directionality of the universe. And there it is. You spot it. The cold spot. A large region of the sky, notably cooler than it ought to be, like a bruise on the face of the cosmos. At first it seems like just another irregularity. Nothing to write home about. The universe, after all, is allowed to be a little bumpy. But the cold spot is too cold, too big, too different. And most importantly, it doesn't quite fit with the random pattern you'd expect from quantum fluctuations in the early universe. Historians still argue whether this cold spot is simply a statistical anomaly, a 1 in a million blip that looks meaningful but isn't. But others think it might be something much more dramatic, evidence of a collision between our universe and another one. Yeah, A whole other universe. Let that one swirl in your sleepy brain for a second. The cold spot lives in the constellation Eridanus, which sounds fancy enough, but it's just a particularly chill part of the sky. Some researchers think the cold spot might be caused by a supervoid, a vast empty region of space with fewer galaxies, stars and matter in general, like a cosmic pothole. As light from the CMB travels through this underdense region, it loses a bit of energy, resulting in that lower temperature we detect. But here's the issue. The void explanation doesn't fully add up. The void isn't quite empty enough to account for the full temperature dip. It's like blaming a weak fan for a sudden Arctic breeze. The math just doesn't close. So back to the multiverse theory we go. Some physicists speculate that if other universes exist, they might occasionally nudge up against ours, like soap bubbles bumping together. These collisions could leave scars in the CMB, cold or hot spots where the fabrics interacted. If that's the case, the cold spot might be more than just a blemish. It might be a bruise left by a neighbouring cosmos. A little fringe, definitely, but not unthinkable. The multiverse is one of those ideas that floats at the edge of science and science fiction. Plausible, unprovable, and irresistibly cinematic. As you glide through the microwave glow, you start to notice something else. The cold spot isn't just a temperature oddity. It seems to align with other features in the CMB. There are long, large-scale alignments across the sky, patterns that shouldn't exist in a truly random, direction-neutral universe. These alignments, as you'll soon see, form something delightfully dramatic called the axis of evil. But don't jump ahead just yet. Instead, listen to the whispery hum of the early universe around you. Scientists have created full sky maps of the CMB using data from missions like COBE, WMAP, and Planck. Each time they refine the image, remove the noise, subtract the Milky Way's influence, and yet these odd features persist. What you're looking at isn't just an aesthetic blemish. It challenges the very idea of statistical isotropy, the notion that the universe looks the same in all directions on large scales. That assumption underpins most of modern cosmology. It's like the foundation of a house, quiet, invisible, taken for granted. But if it's off even slightly, the whole structure starts to lean. Imagine building a puzzle of a blue sky, soft gradients, fluffy clouds, nothing suspicious, but then you notice 3 or 4 pieces with stripes, or smudges, or a directionality to them, and they line up. That's what's happening here with the CMB. Now let's go back, way back, to the actual discovery. Arno Penzias and Robert Wilson were just trying to get rid of noise from their radio antenna. They cleaned bird droppings off it, true story, repositioned it, checked their equipment, and still the static persisted. That static? The CMB. So, yeah, the early universe kind of sounded like background TV fuzz, and even that fuzz it turns out might be directional. Here's a quirky thought. Some indigenous Australian star maps describe patterns in the sky that aren't based on the stars themselves, but the dark spaces between them, shapes made from absence. The MU in the sky, for example, isn't a constellation of stars but a pattern of dark nebulae across the Milky Way. It's a lovely poetic inversion, seeing direction in the void, which feels oddly appropriate for the cold spot and its secrets. So now you're floating, not through stars but through ancient radiation. And you're starting to get the distinct impression that this universe, this supposedly random uniform universe, might have a wrinkle, a lean, a twist, a temperature bruise and a smudge in its symmetry. Of course, not everyone agrees. Some scientists argue that these anomalies are artifacts, glitches from imperfect data removal, or statistical flukes that we're overinterpreting. Others suggest they could be due to local phenomena in our own galactic neighbourhood that contaminate the readings. Maybe we just haven't cleaned the lens enough. But there's something compelling about the idea that the oldest light in the universe, light that has been travelling for nearly 14 billion years, might be trying to tell us something directional, something hidden. You tilt your imaginary head toward the cold spot. It doesn't look threatening, just quieter, dimmer, lonely even. But in the context of everything you've now seen, it feels like the universe blinking at you, like a cosmic wink, or maybe a warning. Either way, the CMB isn't just the baby picture of the cosmos, it's a whisper from its infancy. And you, lucky sleeper, are here to listen. You float just a little farther from the glow of the cosmic microwave background, and you begin to see it. Not just the cold spot now, but a thread, a line, a pattern, not obvious, not dramatic, but undeniably strange. You're tracing your eyes, or maybe your sense of direction, along a subtle alignment in the oldest light of the cosmos. They called it, drumroll, the axis of evil. And no, it's not the name of a forgotten Marvel villain or a rejected Bond plotline. It's a very real, very controversial feature in the CMB, and cosmologists actually use that name, half jokingly and half in exasperation, because what it represents is kind of rude. It refuses to behave like a good little random fluctuation. It lines up, it aligns, and in doing so, it might ruin everything. You're not supposed to find large-scale alignments in the CMB. The early universe should have been chaotic, bubbling with quantum noise, full of tiny temperature differences scattered randomly. But the axis of evil, a strange correlation in the quadrupole and octupole moments of the CMB, suggests a preferred direction across the entire sky. You might be picturing some kind of glowing arrow across the heavens, and while it's not that literal, it's close. When you smooth out the microwave background data, certain patterns don't just appear, they point. They favour one area of the sky, as if the early universe had a front and back, or a top and bottom, or maybe something like a spin. The axis of evil stretches across hemispheres of the observable universe, a sweeping orientation in the CMB's low multipole moments. These moments are like harmonics in a cosmic song, big slow undulations across the sky, like bass notes in a symphony of static. And those bass notes, they're not evenly distributed. They lean, they line up. And here's where things get frustrating, because if true, this axis challenges a major pillar of cosmology, the cosmological principle. That's the idea that the universe, on large scales, is homogeneous and isotropic. Basically, the same in every direction and at every location. No special places, no privileged directions. But this axis? It's the cosmological equivalent of the universe clearing its throat and muttering, well, actually. Historians still argue whether the axis of evil is real or just an artifact of data processing. Maybe it's a statistical coincidence, or maybe it's caused by local structures, our own Milky Way, or nearby galactic filaments, contaminating the signal. Scientists have tried to remove the foreground noise and see what's left, but like a smudge that won't wipe away, the axis persists. One researcher even compared it to finding your cereal spells out HELPME, and wondering if it's coincidence or your cornflakes are haunted. Now, before we throw the entire model of the universe out the window, let's be fair, this doesn't prove that the universe has a preferred direction. But if you're floating out here, staring into the deepest fossil record we have, and you see multiple signals, galaxy spins, temperature anisotropies, strange alignments, it gets harder to just wave them away. You look to the left, there's that cold patch. You turn slowly to the right, there's a mirrored anomaly. You float forward, and the background glow shifts ever so slightly. The axis isn't just visible, it's tangible. A sort of gravitational itch under your skin. This isn't the only time people have tried to find a hidden direction in the universe. The ancient Egyptians aligned their pyramids with true north. Chinese astronomers mapped the stars in careful lines and sectors. Even the Babylonians tracked planetary motion with eerie precision. Humans have always been obsessed with celestial order, and perhaps, just perhaps, that obsession wasn't totally misplaced. Here's a fringe idea to nibble on. What if the universe actually rotated at birth? Not the galaxies within it, but space itself. Some speculative models, mostly rejected but not all, propose that the Big Bang might have imparted angular momentum to the cosmos as a whole, a kind of universal spin. If that's true, it could explain alignments like the axis of evil. It could even account for the handedness of galaxy spins from earlier. And now you might be wondering, if the whole universe is spinning, what's it spinning against? And that's the truly brain-breaking part. There's no outside for the universe to spin relative to, unless, of course, you entertain the possibility of extra dimensions, or a multiverse backdrop, or whatever comes next in this increasingly philosophical rabbit hole. Of course, most physicists aren't ready to light that candle just yet. They prefer caution, more data, better instruments, clean separations between signal and noise. And that's fair. The stakes here are immense. If we confirm a preferred direction in the CMB, it would ripple through physics, astronomy, and even the nature of time itself. But you're already floating in the thought of it. You can feel the tension, like you've walked into a vast room where the furniture looks random, but all happens to face one corner. You want to know what's in that corner, what's drawing everything. Oh, and speaking of coincidences, the axis of evil just happens to line up suspiciously close to the plane of our solar system. That's right. Some skeptics argue that this implies a processing artifact, or maybe even Earth-based contamination of the data. But others raise an eyebrow. What are the odds? Is the axis trying to tell us something about us? You slowly rotate yourself in that direction, aligning your body with the axis like a very confused human compass. It's not pulling, exactly. It's more like a suggestion, a quiet whisper saying, "This way, friend." Some researchers have proposed ways to test whether the axis is real or fake. For instance, if future surveys of galaxies, gravitational waves, or neutrinos show the same alignments, it would strengthen the case. If, on the other hand, it disappears with better foreground subtraction, we might chalk it up to noise. But for now, it's Schrödinger's axis. Possibly real, possibly not, potentially universe-shattering, or just a cosmic prank. You exhale softly, not that you need to breathe out here. The CMB glows behind your eyes, the axis stretching from your crown to your feet, like an invisible thread through your mind. Real or not, it's in your thoughts now. It hums at the edge of your awareness, like a note just out of tune. And maybe, just maybe, you're starting to feel that this universe has a subtle way of pointing. You haven't moved, but the universe shifts around you. Or maybe it's just your perception that's wobbling. Quiet tremor in your understanding. Because all this time, you've been floating in space assuming the universe is fair, symmetrical, a kind of cosmic democracy where every direction is created equal. But let's be honest, that assumption has never really been stress tested. The principle behind this belief is something called isotropy. It's the idea that, on large enough scales, the universe looks the same no matter which direction you face. Turn left, drift right, barrel roll through a galaxy cluster. It should all be evenly distributed, statistically identical in all orientations. It's a comfortable notion. Symmetry is tidy. We like tidy. But as you gaze back toward the axis of evil, the cold spot, and the lopsided galaxy spins, that comfort begins to unravel. Because maybe isotropy isn't a law, it's just a polite assumption we've been clinging to because it makes the math easier. The thing is, our entire cosmological model is built on isotropy. The equations that predict the expansion of the universe, the growth of galaxies, the future of everything, they all start with the assumption that no direction is special. But what if one is? You imagine holding a cosmic dice in your hand, giving it a roll, and seeing it land the same way, again and again. That's not randomness. That's a pattern trying to escape its cage. Historically, this principle of isotropy has been both a revelation and a restraint. Back in 1917, Albert Einstein adopted it to make his first cosmological models work. He assumed the universe was the same everywhere and in every direction, because otherwise the math spun out into chaos. This helped him develop the idea of a static, eternal universe, which we now know is very wrong, but it set the tone for how physicists modelled reality. Even the mighty Big Bang theory depends on isotropy, the idea that everything emerged from a single, hot, dense point and then expanded outward evenly, like dough rising in every direction. Without isotropy, inflation, the rapid expansion phase just after the Big Bang, starts to look suspiciously patchy, like the universe stretched faster in some directions than others. And here's where things get weird. Some cosmologists have started to propose models of anisotropic inflation, a scenario where the early universe didn't inflate evenly. It stretched faster along one axis than another, imprinting a permanent preferred direction into the cosmic fabric. And that preferred direction, it might be what we're seeing today in the CMB alignments and galaxy spins. Historians still argue whether this anisotropic inflation is a useful adjustment or an act of desperation to save a theory that's slowly fraying at the edges, but it's not entirely baseless. In fact, back in the 1990s, a few quiet voices were already suggesting the universe could have some built-in asymmetry. People mostly ignored them, but then came the CMB maps, the cold spot, and the axis no one wanted to name. Now the idea is getting dusted off and reconsidered. Maybe the universe isn't perfectly isotropic. Maybe it never was. You float past a simulation, a mathematical hologram of the early universe. You watch as it balloons outward, expanding unevenly. One axis stretches just a hair faster. That tiny difference ripples forward in time, and billions of years later, you get spiral galaxies leaning the same way, radiation patterns forming an invisible line, and that nagging sense that the universe has a front. Of course, some of this could be coincidence, a cosmic Rorschach test. Humans love finding faces in clouds, stories in stars, meaning in static. You look long enough at a map of temperature fluctuations, and your brain will find a pattern. It's what brains do. A bit like conspiracy theorists connecting thumbtacks with red string, except in this case, the string is made of ancient light, and the thumbtacks are galaxy clusters. Still, the evidence stacks. Even subtle gravitational lensing data, how massive objects bend the path of light, has shown tiny hints of anisotropy. Not enough to convict, but enough to raise an eyebrow, or maybe an Einstein-level grimace. Let's drop down to a more grounded comparison. Imagine standing on Earth, looking out across the ocean. If the Earth were isotropic, you'd expect every horizon to look the same. But what if one direction always had choppier waves, or brighter sunsets? You'd start to suspect something unusual. Now scale that up to the cosmos. If one direction consistently yields different cosmic data, warmer temperatures, more galaxy spins, odd alignments, that's more than just a choppy wave. That's a directional fingerprint. And this isn't the first time symmetry has let us down. Parity violation in weak nuclear interactions, the phenomenon where certain particles prefer a left-handed interaction, was a shocking discovery in the 1950s. Before that, physicists believed the universe had mirror symmetry at every level. But it turns out even nature likes a bit of flair. So if mirror symmetry can break down on the quantum scale, maybe isotropy can break on the cosmic one. Nature isn't always tidy. Sometimes she scribbles in the margins. Here's a fringe theory just for your dreams. What if the breakdown of isotropy isn't an accident, but a message? Some have suggested, half seriously, that a directional bias in the universe could be the result of deliberate design, a cosmic signature, a way to say someone was here. Now that's not a mainstream view. Most physicists will point you to Occam's razor and walk away briskly. But in the hush of a sleepy night, it lingers in the corners of thought like an old perfume. But whether the pattern is natural, accidental, or artificial, the fact remains. The more data we collect, the more smaller symmetries creep in, and the more we pretend not to see them. You spin gently now, testing the universe's fairness. Is that side brighter? Is this side colder? Or is it just your imagination, primed by 3 sections of evidence? Either way, the spell of isotropy is breaking. The belief that no direction matters more than another is being worn thin by observation, slowly frayed by whispers from every corner of the cosmos. And if symmetry can fall at this scale, what else might crumble? You stretch your limbs in zero gravity, aligning yourself with no direction in particular, and wonder, if there is a hidden arrow in the universe, where is it pointing? And more hauntingly, are we supposed to follow it? You drift now, slowly spinning in the black, passing between great sweeps of galaxies and pale curling arms of spiral stars. The silence is perfect, but the universe isn't. You've seen the hints, galaxies spinning more one way than the other, ancient radiation with a secret tilt, an axis nobody asked for. But now you're going to feel it, or at least imagine the feeling of it. A subtle push, like a tide you didn't notice was there. It's time to talk about dipoles, specifically the cosmic dipole anisotropy. Say that 5 times fast in your best sleepy voice, but don't worry, you're already part of it. The idea's simple enough. When scientists look at the cosmic microwave background, you're very familiar with it by now, they notice one half of the sky is just a tiny bit warmer than the other, not dramatically, just by about 0.003 Kelvin. But in cosmology, that's a glaring imbalance. This difference, this dipole, is typically explained by something quite pedestrian: motion. Our solar system, our galaxy, the entire local group is moving through space at roughly 370 kilometers per second. That's over 800,000 miles per hour. And just like how the sound of a car changes pitch as it passes you, hello, Doppler effect. The CMB appears slightly hotter in the direction we're heading and slightly cooler behind us. You feel that? That's the warmth of your future rushing toward you, and the cold trail of your past slipping behind. So far, so good. The dipole is expected, but there's always a but, isn't there? See, researchers have gone further. They've compared this cosmic dipole to other measurements, not just the CMB, but the distribution of galaxies, the movement of galaxy clusters, the radio sky, even quasar populations. And here's where the discomfort sets in. Many of these observations show extra dipoles, patterns that can't be explained by our motion alone. In other words, we're seeing anisotropies that don't line up with what we should expect, even after accounting for our movement. Historians still argue whether this means our understanding of motion through the cosmos is incomplete, or if these dipoles hint at a deeper hidden structure. Could the universe itself have a motion? A flow? An intrinsic slant? Let's get a little technical but stay cozy. The dipole in the CMB is the largest anisotropy we see. All the smaller bumps and wiggles, the cold spot, the axis of evil, are built on top of this. But when you subtract the motion-induced dipole out of the data, you expect the rest to look fairly directionless. Instead, more patterns keep popping up. It's like peeling an onion and finding more onions, all of them slightly lopsided. A controversial paper in the 2010s suggested that the observed dipole in the number counts of galaxies doesn't align perfectly with the motion-inferred dipole from the CMB. That's weird. because those two should match if the CMB dipole is entirely caused by motion. But what if it isn't? What if part of the dipole isn't from our movement at all, but from a real asymmetry in the fabric of the universe? You tilt in space, facing the hot direction. That way lies the constellation Leo. You can't feel the heat, of course, but you imagine a faint pressure, as if the universe is gently nudging you forward. Then you turn slowly around to the cold side. Behind you, the photons are slightly less energetic, the echoes of the Big Bang retreating into the distance. This isn't just an abstract debate. If the cosmic dipole has intrinsic components, if it's built into the universe itself, it would mean our whole coordinate system needs adjusting. The cosmological frame of reference isn't as neutral as we thought. And it gets weirder. Radio surveys from telescopes like the NVSES, NRAOVLA Sky Survey, have found that radio sources, distant active galaxies, also show a dipole alignment, but not the one we expected. The radio dipole is stronger than it should be, too strong, like the universe is broadcasting in one direction more than another. You ever stare at a campfire and notice that one side always sends more sparks? That's what this feels like. Except the campfire is 93 billion light-years wide, and the sparks are ancient photons and galaxies. Fringe theorists, and let's be honest, some very respected physicists too, have started to wonder whether these excess dipoles are signposts. Maybe they're hints of something beyond our observable universe, something pulling at us, distorting our view of the cosmos like heat waves on a summer road. One candidate, the ever-enigmatic dark flow. But let's not get ahead of ourselves. That current runs deep, and we'll float into it next. For now, picture this. You're standing on a moving walkway in a massive airport. You're moving fast, yes, but what if the floor itself is also moving? And what if, somewhere ahead, there's a tilt to the entire building? That's the sensation here. Our motion through the universe is real, but the ground beneath our cosmic feet may also be shifting. And here's your quirky historical tidbit for the night. Back in the 19th century, physicists believed in something called the luminiferous ether, a supposed medium that light waves needed to travel through, like air for sound. It was eventually debunked. Thanks, Michelson and Morley. But the idea that space might have structure, a frame, a direction, never quite died. It's just taken on new forms, better dressed and less Victorian. You can feel it now, can't you? The subtle tilt. The sense that some directions in the universe might be more than just coordinates. They might carry energy, momentum, information. Even in sleep, the mind craves orientation. Left or right, up or down, toward or away. It's how we built compasses and later GPS. But if the universe itself has a cosmic north, then maybe we've all been drifting without knowing what we're truly heading toward. You stretch your arms into the hot side of the dipole, imagining the gentle pressure of ancient photons against your skin. A breeze that's been blowing since the dawn of time, and somewhere behind you, in the cooler direction, the universe exhales. It's not motion you can feel, but it's motion you can suspect, and suspicion, in science, is often the beginning of truth. You turn your imaginary body into the breeze, not the solar wind, not the soft ripple of background radiation, but something deeper, heavier, and harder to name. It feels like a current under your feet, not quite gravity, not quite motion, just flow. And now you find yourself face to face with one of cosmology's most unsettling concepts, dark flow. Sounds like a moody jazz album or maybe a suspicious brand of energy drink, but it's actually a real term used by real physicists to describe something we don't fully understand. A mysterious drift observed in the motion of galaxy clusters, huge, gassy, star-dense cities in the cosmos, all seemingly moving in the same direction. together, like a cosmic traffic jam heading toward nothing we can see. You're floating above one of these clusters now, maybe the Norma cluster or Abel 400, and you watch it slide quietly through space. You think it's just gravity pulling it along, until you realize it's not moving toward anything we can detect. It's moving toward a region of sky that contains no massive attractor, no galaxy supercluster, no dark matter over density that we know of. Just movement, direction, flow. The story of dark flow begins in the 2000s, when researchers used data from NASA's WMAP mission to examine the kinetic Sunyaev-Zeldovich effect, which, don't worry, is not a spell from a Russian wizard, but a phenomenon where moving galaxy clusters distort the cosmic microwave background slightly due to their motion relative to the CMB. In short, you can measure how big galaxy clusters are moving based on how they mess with ancient light. What they found was unexpected. Clusters across vast swathes of the observable universe appeared to be drifting in the same direction, a motion that couldn't be explained by gravity alone. Not local gravity, not even large-scale structure. They seemed to be pulled toward a point beyond the edge of the observable universe, somewhere past the constellation Centaurus. Like leaves floating toward a drain you can't see. Historians still argue whether dark flow is real or just a mirage caused by miscalculated data or instrument limitations. Some scientists have challenged the findings, arguing that the signals are weak, statistical noise dressed up as drama. Others insist the pattern is too coherent, too wide-reaching, too weird to ignore. The potential explanations for dark flow, if it's real, are frankly wild. One possibility? A massive structure beyond the cosmic horizon. A region of space we can't see because light from it hasn't had time to reach us yet, but which is nonetheless affecting our universe gravitationally. Imagine a massive wall or a concentration of mass, a super universe-sized attractor that tugs on our galaxy clusters from the other side of the observable limit. Something impossibly vast, but forever out of sight. Like standing in a small room and watching all the furniture lean slightly toward one corner, even though the wall looks flat. Another explanation? A bubble collision. If our universe is just one bubble in an eternally inflating multiverse, maybe another bubble bumped into us long ago. The result could be a residual directional push, an ancient collision that still echoes in our motion. If so, dark flow might be the fingerprint of a sibling universe that shoved us on its way out. And then there's a more fringe idea, that space-time itself is lopsided, that the very geometry of the universe is warped in such a way that mass flows in a particular direction naturally, like water down a sloped sink. If true, this would break the cherished notion of isotropy, yet again, and suggest that the universe isn't just expanding, but slanting. You rotate slowly, trying to feel it. The invisible pull, there's no roar, no tremor, but the stars ahead of you, clustered, tangled, moving, seem to whisper the same word, this way. The concept of a preferred direction on this scale is deeply unsettling to cosmologists. It makes the universe feel less like a smooth balloon and more like a conveyor belt, or worse, a tide pulling us towards something from which there is no return. And yet the data won't go away. Even newer CMB observations from Planck have not entirely ruled out the existence of dark flow, though they've muddied the picture with questions of foreground contamination and analysis techniques. You might be wondering, why haven't we just gone and looked in that direction? We have, and we didn't find much. That's part of the problem. There's nothing obvious there. No monstrous cluster of galaxies, no massive wall of dark matter, no visible structure to explain why entire regions of the cosmos are moving that way. It's like standing on a boat and feeling it drift, but looking out and seeing only flat, endless ocean. Of course, some skeptics say it's not drift at all. It's our measurement tools playing tricks. They argue the signals are artifacts, nothing more. But others maintain the flow is real, that it's not just statistical noise, that the alignment across scales is too strange to be a coincidence. Want a quirky historical echo? Ancient Polynesian navigators used stick charts, wooden maps that showed ocean currents and wave interference patterns invisible to the eye. They read the sea by its texture, its push and pull. In a strange way, dark flow feels similar, a directional current inferred not by what we see, but by what we feel in the data. You turn again, drifting with the flow, as if to let it carry you. It's not violent, not urgent, but it's there, like an unseen hand gently guiding entire clusters of galaxies forward, like a message embedded in the motion. One fringe interpretation even imagines the universe as a brain, a four-dimensional surface floating through a higher dimensional space. In such models, our universe could be passing near another massive structure, causing a gravitational tide in the form of dark flow. Sounds like science fiction? Absolutely, but it's in the papers, the math checks out. And that's how science works. You throw your mind at the wall of the unknown and see what sticks. As you follow the flow, you can't help but wonder, if all these galaxies are heading toward a point we can't see, what happens when they get there? Is there a cosmic event waiting at the end of the current? A great attractor beyond all attractors? Or is this just motion without meaning, like leaves in the wind? You let yourself drift, giving into the pull, and in the silence of the void the thought arises like a tide. If the universe has a current, then maybe direction isn't just an illusion. Maybe space remembers where it came from, and maybe it's trying to go back. You're still coasting through that unseen current, galaxies gliding past like silent sentinels. That gentle, unexplained motion, dark flow, has you wondering if maybe our universe is just one eddy in a much larger sea, a sea with waves, tides, and other bubbles floating nearby. Tonight, we take a sleepy dive into one of the most deliciously bizarre possibilities of modern cosmology: bubble universes. No, not bubble tea, not bubble wrap. We're talking about entire universes, maybe an infinite number of them, each floating in a foamy multiverse, separated by expanding nothingness and occasionally perhaps brushing against each other in ways that leave marks. Marks like galaxy drift, like the cold spot, like that unsettling feeling that the universe has a direction because something nudged it long ago. So let's rewind a bit. In our current understanding of the early universe, right after the Big Bang, there was a brief wild moment known as cosmic inflation, a flash of expansion so rapid it makes dark flow look like a lazy Sunday stroll. The theory goes that this burst of growth smoothed out the early chaos and explains why our universe looks so flat and uniform. But here's where things get speculative, and honestly, fun. In many versions of inflationary theory, that inflation doesn't stop everywhere at once. Instead, it continues in other regions of the broader multiverse, creating pockets where inflation slows down and a bubble forms. Each bubble, a universe, maybe with different physical laws, maybe with more dimensions, maybe with absolutely no pineapple pizza. You, lucky sleeper, just happen to live in one of these bubbles, the one where life emerged, stars formed, and where you can drift off while contemplating impossible ideas. But if we're in a bubble, that means others might be nearby, and sometimes bubbles collide. Think of foam on the surface of a cappuccino. Bubbles expand, jostle, merge, or sometimes burst when they get too close. Now scale that idea up by, infinity. If another universe bubble brushed against ours in the early moments after the Big Bang, it could have left an imprint, a scar, a disruption in the smoothness of space-time. And one of the biggest suspects for such a scar? Yep, the CMB cold spot, the same anomaly you floated past 2 sections ago. Historians still argue whether that cold spot is a random fluctuation, a giant cosmic void, or something far more exciting, the sign of a past collision. A place where another bubble slammed into ours, injecting its weirdness, leaving a dent in the microwave background and maybe, just maybe, tipping the universe slightly in a preferred direction. You turn your attention toward the cold spot again. What if that direction, subtly reinforced by galaxy spins, dark flow and CMB alignments, is actually the impact vector from a bubble that passed too close? That would make this preferred direction a kind of birthmark, a bruise from childhood, not an intrinsic asymmetry, but a scar. The universe, in this view, isn't lopsided by nature, it's lopsided by experience. And here's where things get wonderfully speculative. Some multiverse models suggest that bubble collisions might not just happen once. They could keep happening. Maybe there's a constant gentle pressure from another universe brushing against ours, slowly pushing everything in one direction. Or maybe multiple universes are piled around us, each exerting their own influence, like gravitational fingerprints pressing into our bubble from beyond the veil. And if that doesn't scramble your sleepy neurons, try this. In some models, these bubble universes could even contain different versions of you. Maybe in one, you're listening to this line upside down in a bathtub full of glow sticks. Maybe in another, you're a cloud of plasma drifting between stars, wondering if solid things are real. Of course, this is fringe territory. Fun, fertile ground for speculation, but deeply difficult to test. Detecting a bubble collision from billions of light years away is like trying to prove your window has a smudge because your neighbour's house leaned against it briefly 13 billion years ago. Still, there are attempts. Scientists have tried to model what a bubble collision would look like in the CMB. They've run simulations. They've combed the data from WMAP and Planck, looking for the telltale ring-shaped disturbances or disc-like features such an event would leave. Some say they found candidates. Others say, hey, looks like noise. It's the cosmological version of Bigfoot footage. Fuzzy, disputed, and endlessly fascinating. Here's a quirky historical parallel for you. In ancient Hindu cosmology, the universe was said to undergo repeated cycles of creation and destruction, with countless other worlds existing beyond our own, floating in an infinite cosmic ocean. Sounds suspiciously like an early multiverse model, doesn't it? Humanity's imagination has been blowing past the boundaries of its visible sky for thousands of years. But back to your bubble. If another universe did collide with ours, did tip us ever so slightly, it could explain a host of modern mysteries. The directionality in galaxy spins, the asymmetry in the CMB, even that disobedient dark flow. Like rolling a marble across a tilted table, the whole structure might lean, just a little, but enough to matter. Of course, there's a darker possibility too. If bubbles can collide, what happens when one crashes through? Is that the end? Would physics unravel? Would we notice at all? Or would our entire observable universe blink out before we had time to name it? Sweet dreams. But don't worry. According to the best calculations, collisions like that are rare and would have had to happen near the beginning of time. If they're still happening, well, they probably aren't targeting you personally. Probably. For now, you let yourself float within this bubble of a universe, knowing it's one among many. You picture it as a transparent sphere, expanding into the void, brushing elbows with its siblings, maybe sharing secrets, maybe colliding in a great cosmic mosh pit, and somewhere along the edge, maybe one left a mark. Maybe that's the direction you keep turning toward. Not north, not up, but before. A vector written into the structure of the universe, pointing to the place where we were touched, tilted, reminded we aren't alone, So the next time you gaze up at the stars and feel like you're being pulled in a certain direction, maybe you are. Maybe it's the echo of a collision that happened before time had names. Or maybe it's just your blanket slipping off the bed. Either way, roll back over, tuck in tight, and remember, the universe might not be centered on you, but it might still be pointing somewhere. You drift farther now, past galaxies and gas clouds, past the conceptual ripples of bubble collisions and cosmic bruises, and into something stranger. Stranger because it's closer. Stranger because it feels like a trap disguised as nothing at all. Tonight you float into the idea that space itself might be shaped in a way we haven't noticed. Not just curved, shaped, folded, looped, possibly directional. It starts with a simple question. What shape is the universe? You probably imagine something balloon-like, maybe a giant sphere, or a flat, endless grid. That's fair. Those are the standard possibilities. But there's another possibility, one that cosmologists entertain quietly, and mathematicians whisper to each other like a secret handshake. What if the universe is a torus? Yes, a donut. A three-dimensional torus, not with jelly sadly, but with some very weird implications for directionality. In this version, space isn't just expanding outward from a central point, it's wrapped around itself, like a video game map that loops when you walk far enough in one direction. Go far enough north, and you come back from the south. Same with east and west. A toroidal universe means you could theoretically fire a beam of light and have it hit you in the back, given enough time, and a very good aim. Here's the fun part. This kind of geometry could create the illusion of a preferred direction. If the fabric of space loops around in certain ways, then the universe wouldn't be truly the same in all directions. Some paths would be shorter than others, some would intersect themselves, and some, just a few, might subtly distort the way galaxies align, or how radiation echoes through the void. You can feel it now, right? That invisible wrapping. Like the room you're in is bigger on the inside but still somehow folding back into itself. Historians still argue whether such exotic shapes are even testable, but the idea isn't just a stoner thought experiment. Scientists have actually tried looking for repeating patterns in the cosmic microwave background, like looking for wallpaper seams in the sky. The hope is to find matching circles where light has travelled all the way around the universe and come back from the other side. So far, nothing conclusive. But the search continues. Even more exotic than a torus is the idea of topological manifolds, twisted, compact, multiply connected spaces where geometry itself might bend in non-intuitive ways. Space might be knotted, or tessellated like Escher art, or wrapped in shapes we can't visualize without hallucinating. One popular contender in this geometrical gallery is the Poincare dodecahedral space, a kind of 12-faced, slightly twisted universe, where you could, again, potentially see your own back given enough time in the right direction. It would produce specific patterns in the CMB. Some researchers claim the observed low-power anomalies in the background radiation, remember those awkward alignments, might actually fit with this model better than the standard infinite flat universe. Of course the math gets heavy here, so let's step lightly. You don't have to understand all the tensors and eigenvalues to imagine this. A universe that, by its very shape, subtly tells you which way to go. Not because of gravity, not because of another universe pushing, but because geometry itself is directional, like how a Mobius strip has only one surface, yet also a built-in twist. Fringe theorists, and some serious ones too, have speculated that these shapes might explain some of the cosmic asymmetries we've seen. The cold spot, the axis of evil, the dipoles. What if they're all just artifacts of a weirdly shaped space that loops and folds in ways our instruments haven't caught yet? You start to think about how GPS satellites orbiting Earth have to account for general relativity. Time ticks differently depending on gravity. Imagine what weird geometries would do to light, to mass, to our perception of straight versus curved. In a twisted space, light might take strange paths, and matter might subtly favour one direction over another without us noticing for billions of years. Want a quirky parallel? The ancient Greeks once believed the earth was flat, then spherical, and eventually that the heavens moved in perfect circles. But Pythagoreans flirted with the idea that the entire cosmos was shaped in harmony, its form driven by mathematical beauty. They were wrong about the details, but right about the question: what if shape matters more than we think? Because if the universe is folded like origami, then maybe what looks like directionality is really just us staring at the crease. Here's the kicker: if space has a global shape, something finite yet unbounded, it could also have symmetries and axes built into it, directions that loop faster or take longer to return, directions that light prefers. These could give rise to the subtle patterns we've been seeing, not because something pushed the universe, but because the universe was built that way. And now you're floating again, arms out, drifting toward a loop you can't see. You wonder, if you just kept going, would you arrive where you began? And would you be the same? Another possibility, anisotropic expansion. If space is shaped in a way that stretches more in one direction than another, say, elongated like a cosmic ellipsoid, then you'd have a built-in preferred direction. That's not isotropy, that's baked-in bias. Some models, like the Bianchi cosmologies, explore this idea. Bianchi Type 1, for example, allows for expansion at different rates along different axes, and when researchers overlay these models onto CMB data, they actually get a slightly better fit in some regions than the standard model. But that extra precision comes at a cost: more parameters, more complexity. So mainstream science still mostly keeps these models on the fringe. Still, if space is shaped with a twist, then everything inside it, light, gravity, galaxies, you, might be flowing slightly downhill, following the grain, like dust motes drifting on the surface of a bowl. You run your hands through this invisible grain now. It's subtle, but it's there. Not gravity, not motion, just texture. You remember walking through tall grass, noticing how it bends slightly in one direction from wind you don't feel. That's what this is like. The cosmic field, bent ever so slightly. Not enough to push, just enough to guide. So maybe the universe isn't pointing in a direction because something happened to it. Maybe it always pointed that way, because that's how it's built. The further you drift, the quieter it gets. Not in sound, there's never been much of that out here, but in the feeling of quiet, as if you've slipped beneath the surface of the cosmos into something small, subatomic and buzzing just beneath the noise. You're not above the galaxies anymore, you're between the particles now. And here you find something weirder than gravity, older than light, and far more jittery than you were expecting. Quantum foam. Imagine space not as smooth, black emptiness, but as a constantly fizzing soda, tiny bubbles popping in and out of existence, faster than you can track. This is the quantum foam, the idea that at the smallest possible scale, the Planck length, about 10 to the negative 35th meters, space-time itself isn't smooth, but violently chaotic. It seethes with microscopic wormholes, fluctuations, virtual particles, tiny, twitchy distortions of reality. You float down, down, down into that realm now, and what you find might be more directional than you expected. Because if space-time has a foam-like structure on the smaller scales, who's to say that foam is perfectly uniform? What if even here, in this wild and frothy basement of the universe, there's a bias, a lean, a microscopic tilt that somehow scales upward? It sounds like madness. After all, quantum fluctuations are supposed to be random, governed by chance and uncertainty. But some theorists have suggested that the foam may have statistical structure, not predictable per se, but biased. And if that's true, It could imprint a preferred direction in the way energy, matter, and even time behave at higher levels. One fringe idea is that the quantum vacuum, what we casually call empty space, might not be perfectly isotropic, that it has anisotropic energy densities. Think of a dance floor that looks flat but has a very subtle slope. The dancers don't notice at first, but over time they tend to drift in one direction. Same idea here. Particles may not know there's a slant in the vacuum, but their behaviour, summed over billions of years and billions of light years, might just start to show it. Historians still argue whether quantum foam is a real thing, or just a placeholder for something we haven't figured out yet. It was first seriously proposed by John Wheeler in the 1950s, the same guy who helped name black holes and thought time might be an illusion. So, a big thinker. Some interpretations of quantum gravity, especially loop quantum gravity and certain flavours of string theory, suggest that the foam is real and potentially measurable. Not with your backyard telescope, but maybe by looking at how high-energy particles or light rays behave over enormous distances. Here's the thing. If there's a directional bias in the foam, photons travelling through space should accumulate tiny directional preferences, like rain drifting diagonally in a storm. Over billions of years, the patterns could show up in subtle polarizations, small shifts in particle decay rates, or even the alignment of distant quasar jets. And some researchers think we're already seeing hints of this. Take vacuum birefringence, for example, a predicted phenomenon where light travelling through the quantum vacuum behaves differently depending on its polarization. Like how polarized sunglasses filter sunlight differently depending on angle. If the vacuum itself has a built-in texture, then light should experience that texture, and the result would be a tiny but measurable preference in direction. Even more intriguing, certain experiments involving ultra-high energy gamma rays from distant galaxies have shown tiny anomalies in how light arrives. These aren't smoking guns, but they're suspicious. As if the fabric of space-time itself has a grain, and photons travelling against that grain get just slightly frayed at the edges. Want a quirky parallel? In 14th century Islamic astronomy, the scholar Nasir al-Din al-Tusi proposed a system of celestial spheres that twisted in alternating directions to explain planetary motion, like cosmic gears with friction. His model wasn't exactly right, but the instinct was there, that even the heavens might have structure beneath structure, twisting layers within twisting layers. Now fast forward to today. Some physicists wonder whether the Planck scale foam might act like one of those gears, churning beneath everything, imposing a direction not from above, like a push, but from beneath. Like a river's current you only notice after floating for hours. And if that's true, if this substructure carries a built-in direction, then our entire universe might be subtly aligned from the ground up. It wouldn't be dramatic. The bias would be almost undetectable in everyday physics, but over cosmic distances, over the age of the universe, it might lead to the very patterns we've been seeing, the dipoles, the axis, the spin preferences. A slow, soft whisper from the bottom of everything saying, "This way." Of course, no one agrees on the exact mechanism. Some think it's the result of initial conditions at the Big Bang. Others think it could be due to quantum anomalies, tiny violations of symmetry that bubble up like imperfections in crystal. And then there are the really speculative ones. The thinkers who suggest that quantum foam might be entangled with something outside our universe. Some kind of metastructure where our random fluctuations are part of a bigger pattern we can't see. Like being inside a snow globe and not knowing someone's been shaking it with a leftward twist this whole time. Even in mainstream science, there's an open question. Is the vacuum really empty? Or is it seething with structure and bias we just haven't tuned our instruments to detect? You pause here, hovering at the Planck scale. Not really small, not really large, just infinitely strange. and you start to get the feeling that maybe direction isn't something added to the universe. Maybe it was never not there. You trace the tiniest ripple in space with your finger, imaginary or otherwise. It leads somewhere. Everything does. And maybe that's the truth hidden inside the foam, that the universe always had a lean, a preference, not loud, not forceful, just persistent. Like a trail through snow, long buried, still guiding your steps. You float back up now, not in space exactly, but in scale. Up from the plank-length squirm of quantum foam to the smoother flow of classical space-time, where things behave more politely, at least most of the time. But tonight you're stepping into a concept that breaks all the polite rules. Because what if you could move faster than light? You're not supposed to, obviously. That's the cardinal rule of physics. Nothing travels faster than light in a vacuum. Einstein signed that law in ink, and physics hasn't dared erase it. But some particles don't seem to care. Or rather, some theories say they wouldn't, if they existed. Say hello, cautiously, to tachyons. Tachyons are hypothetical particles that, if real, would always move faster than light. Not sometimes, not by accident, always. They're the rebellious middle children of the particle zoo, completely theoretical, possibly imaginary, and wildly problematic. You hover in a field of what-ifs now, watching tachyons streak past faster than light, faster than your thoughts, leaving behind a trail of implications. One of the most fascinating things about tachyons is that they reverse causality. In some reference frames, they'd arrive before they were emitted. Yes, time travel in particle form. Imagine throwing a baseball that lands before you wind up. Tachyons mess with the order of events, making physicists squirm and philosophers giddy. And here's where it gets even stranger. If tachyons exist, they might move preferentially along certain directions in space-time. Theoretical models suggest that tachyonic fields could carry a kind of built-in orientation, an arrow through the vacuum. Not just through time, but through space. A directional gradient of possibility. You stretch your hands into this conceptual stream, and for a moment you think you feel it. The rush of particles that shouldn't be there, moving along a track the rest of physics pretends doesn't exist. Now, to be clear, no tachyon has ever been observed, and many physicists believe they can't exist, not because we haven't found them yet, but because their existence would fundamentally violate the way we understand causality and stability. In many models, they show up as mathematical ghosts, instabilities in a system rather than real particles you could say, put in a sandwich. Still, some versions of string theory have flirted with tachyon-like objects. In these theories, a tachyon field represents a kind of unstable potential, a slope that particles roll down until the system stabilizes. This roll, this decay, carries direction, a sort of built-in arrow. And there it is again, direction. Historians still argue whether tachyons should be taken seriously or filed alongside other delightful doomed ideas like phlogiston or the luminiferous ether. But they keep showing up, because in a universe with asymmetries, directional anomalies, and possible violations of isotropy, tachyons offer a tool to explain motion that isn't quite allowed. Want a quirky bit of tachyon trivia? In 1967, physicist Gerald Feinberg proposed that if tachyons existed, they might have imaginary mass. Not imaginary as in made up, but imaginary as in involving the square root of -1. Which just adds to the surreal feeling that tachyons belong more to dreams than equations. But surreal or not, their behaviour fits neatly into a cosmos with built-in directions. Because here's the thing, in relativity, space and time are part of the same fabric. So when you talk about a preferred direction in time, you're automatically hinting at a preferred direction in space. That's where tachyons come in. If they exist, they might indicate not just when things happen, but where they want to go. You slowly spin in your imaginary space now, thinking about time. You've always known it flows forward, But does it? And is it flowing at all? Or are we just moving along a pre-existing direction, the way a bead moves along a wire? Some physicists believe that time's direction, the so-called arrow of time, comes from entropy, the universe's tendency to move from order to disorder. But entropy itself has spatial implications. If the early universe had low entropy and it's increasing in a specific way, then that change could suggest a larger, directional structure that includes both time and space. So maybe, just maybe, tachyons aren't fictional particles. Maybe they're remnants, like tiny time surfers still riding the original wave of the Big Bang. And if they still follow that ancient path, then maybe that path is the source of the cosmic direction we've been tracking since Section 1. You're beginning to notice a pattern, aren't you? Galaxy spins, CMB alignment, dark flow, quantum foam, and now time itself, through the lens of hypothetical faster-than-light particles, might also be directional. And this all raises a sleepy but profound question. What is direction, really? Is it a label we put on space, a coordinate in a system, or is it something deeper? Something that emerges from the structure of the universe, not just the large-scale map, but the fundamental rules beneath the map. And here's where the tachyons leave you with one last mystery. Some speculative physicists believe that if tachyon fields exist, they could form cosmic vector fields, fields that literally have a preferred orientation in space-time. These would create a kind of cosmic wind, detectable not by force but by statistical drift. More particles aligning one way than another, more energy flowing east than west, more light twisting one way through the void. In that model, directionality isn't an accident. It's a consequence of structure, a silent universal whisper. Like a background melody the universe has been humming all along. You drift in that silence now. No tachyons flicker past, of course. You're not equipped to see them. But you feel the hypothetical breeze, and you remember every forbidden idea was once an unproven one. Maybe direction is written not in stars but in the gaps between particles, in the impossible routes, the ones that light can't take. And maybe, if you could go faster than light, you'd see the universe's true compass at last. But tonight, you settle for drifting, forward. Maybe. You leave the whisper of tachyons behind, if they were ever there at all, and rise once more into the rhythm of space. But now, instead of watching galaxies spin or background radiation glow, you listen. Not with ears, with imagination. Because the universe hums, and sometimes that hum has a twist. Tonight you're riding the ripples, gravitational waves. These are not just poetic metaphors. Gravitational waves are real, confirmed by LIGO in 2015, when it detected the faint shudder of two black holes colliding over 1 billion light-years away. Not light, not particles. Just ripples in the actual fabric of space-time. You're floating on them now, like a lazy surfer riding the wake of some ancient cosmic crash. But here's the strange part, the part that brings us back to direction. Because in some theories, gravitational waves don't just stretch space, they can twist it. Like a corkscrew rippling through a sheet. This twist is called gravitational wave polarization, and in certain models, especially those involving extra dimensions or broken symmetries, that twist may have a preferred orientation, which means space might vibrate more easily in some directions than others. Now, the standard view in general relativity gives us two types of gravitational wave polarizations. Think of them like two ways the fabric can wiggle. But more exotic theories, like those that extend or modify Einstein's work, predict more types. And these additional modes could carry vectorial or scalar components, ways the universe might prefer to oscillate. You float through one now, a subtle spiral ripple tugging ever so slightly to your left. It's like riding through molasses with a swirl, not enough to knock you off course, just enough to make you wonder whether gravity has a dominant hand. Historians still argue whether these additional polarizations exist, but recent experiments, including those with LIGO, VIRGO and KAGRA, are designed to test them. If we ever detect non-standard polarizations, it could mean gravity behaves differently in different directions, which again should not happen in a universe that respects isotropy. But what if it does? What if there's a direction in which space prefers to ripple, a cosmic grain, a gravitational wind tunnel? And here's the even spookier thought. What if gravitational waves from certain parts of the sky arrive differently than from others? Not because of the source, but because of the medium they move through, space itself. In some speculative models, especially those involving cosmic strings or primordial anisotropies, gravitational waves might be distorted by large-scale directional structures left over from the early universe, like bumps in the road or walls in the wind. That means the way space shakes could be subtly biased depending on where the wave came from and which way it travelled. Want a quirky analogy? In the 18th century, violin makers like Stradivari selected spruce wood not just for beauty, but for grain direction. The wood structure affects the vibration. So too might the grain of space-time, its quantum or geometric structure, influence how gravitational waves propagate. You're now gliding beside one of these waves, stretching and compressing gently, like riding the belly of a sleeping beast. You imagine waves coming from all directions, and yet some just feel different, sharper, smoother, tilted. The difference is minuscule, like trying to detect mood from a breath, but it's there. Here's where it gets truly speculative. Some researchers propose that a primordial gravitational wave background, analogous to the CMB, might hold hints of a preferred direction. This ancient gravitational noise, generated moments after the Big Bang, could still be washing over us. And embedded in that ocean of ripples could be an alignment, a twist, a vector. In theory, future space-based detectors like LISA, the Laser Interferometer Space Antenna, might be sensitive enough to find it. If so, we'd be looking at a kind of gravitational axis, an orientation baked into the way space itself shudders, one that doesn't rely on galaxies or light or temperature, one that's written directly into the breath of the cosmos. Of course, skeptics argue we're nowhere near detecting such subtleties. They say the data's too noisy, the source is too chaotic, the interpretation's too biased, but still, the models persist. And deep in those equations, something keeps cropping up. Directionality. Even in gravity, even in waves. You drift again now, letting the invisible oscillations pass through you. You feel no pain, no pressure, just a stretch, a squish, and maybe, just maybe, a subtle rotation. Like space isn't just shaking, it's twisting. And that twist, if it's real, could link back to the other strange phenomena you've seen. Galaxy spins, CMB alignments, dark flow. Could all these oddities be symptoms of an underlying gravitational asymmetry? A twist in the very structure of reality? Here's a curious historical echo. Léon Foucault in the 19th century built a swinging pendulum to prove Earth rotates. It moved in a direction that defied expectation, revealing our planet's secret motion. Maybe these gravitational waves are our pendulum, swinging in a plane we hadn't noticed, pointing quietly toward a universal truth we forgot to check for. What if the whole universe is swinging, and the direction it's swinging in, that gentle corkscrew ripple, barely detectable, buried in the hum, is the same direction you felt since Section 1? It would mean gravity, the quiet sculptor of stars and planets, is also carrying a message. Not a shout, not even a whisper, just a frequency. And if you could listen long enough, if you could ride that wave long enough, maybe you'd hear what direction the universe was always meant to go. The gravitational wave hum fades behind you, like the echo of a dream you half remember. You drift higher again, metaphorically, cosmologically, towards something more intricate, more stringy. The universe no longer feels like a flat canvas or a stretchy membrane. Now it feels like it's made of music. Because if gravity reveals a twist in space, then string theory might be hiding the entire orchestra. You float now through an impossible lattice, vibrating filaments stretching in and out of dimensions you can't see. Welcome to the world of strings, where particles are not points but tiny loops of energy, vibrating at different frequencies to produce the particles and forces that make up everything. And here, in this tangled ballet of theoretical physics, you find a new kind of directionality, one that doesn't just bend space or twist gravity, but could actually come from hidden dimensions curling in specific ways. In string theory, particularly its many versions like type 2a, type YB, heterotic, M theory, yes, it's a whole zoo, the universe isn't made of 4 dimensions but 10 or 11. The extra ones are just curled up so tightly that we can't perceive them. They're like the fine print in a cosmic contract we forgot to read. But these compactified dimensions aren't necessarily symmetrical. Depending on how they're folded, they might introduce directional bias into our 3D world. Think of a paper rolled into a cone instead of a tube. That shape has a direction, a point of convergence, and if our extra dimensions are folded like that cone, they might be pointing, not metaphorically, literally. The twist of these hidden spaces could influence the orientation of fields, particles, even the way galaxies form. You run your hand across this unseen shape. You feel nothing at first, then maybe a pull, a lean. Like the shape of space underneath space is slightly warped. Historians still argue whether string theory is science or speculative art. Mathematically beautiful, yes, but hard to test. No evidence yet for strings, no direct proof of extra dimensions, but still, the theory offers tantalizing possibilities for preferred directions embedded in geometry itself. Some versions of string theory include objects called branes, multi-dimensional membranes that float in a higher dimensional bulk. You, and everything you know, might be stuck to one of these branes like a moth on a trampoline, but the brain itself? It could be angled, tilted within the bulk. That tilt could introduce a directional vector, one we experience without realizing it. In fact, certain brain cosmology models suggest that the early universe might have expanded differently along different brain directions, creating long-term anisotropies in matter distribution, radiation patterns, or gravitational behavior, which sounds a lot like what you've been watching unfold across this sleepy journey. You're beginning to see the connections, aren't you? It's not just that galaxies spin oddly, or that gravity twists, or that background radiation leans. It's that maybe all of this is the result of something beneath, something deeper, not a force, not a collision, but a structure. Want something extra strange? There's a concept in string theory called flux compactification, where the way extra dimensions are curled involves field lines, like magnetic lines wrapping around the shape. And depending on the configuration, these fluxes can break symmetry. They can lock in directional preferences, like locking a gear into one groove. The universe, from its very birth, might have been shaped to prefer certain orientations of particles, fields, and expansion. You start to see the universe as less of a stage and more of a machine with grooves worn into it, a factory built not to be neutral, but to favour one output over another. Quirky historical aside. Ancient Hindu cosmology once envisioned the universe as resting on the back of an infinite serpent, coiled and vibrating, holding the world in balance through its oscillations. Sounds suspiciously stringy, doesn't it? Some modern physicists also propose anisotropic string vacua, versions of the universe where the vacuum itself has directionality due to the way strings and branes interact. These vacua might produce different physics in different directions. Imagine a loaf of bread that rises more on one end than the other. If space-time is the dough and string interactions are the yeast, then even the rise of the universe could be lopsided from the start. Now, to be fair, most of this is still theoretical. String theory is notoriously hard to test because the scale is so small and the energy required is so high, but that hasn't stopped the math from suggesting that space itself may not be uniform, and that its hidden structure might carry hints of orientation, handedness, and alignment. What if we're seeing the residue of this structure in our big visible universe? What if the axis that seems to run through CMB alignments, galaxy spins, and gravitational wave polarizations is actually just the projection of a curled, directional manifold from an extra dimension? You close your eyes now, imagining a great twisted staircase, wrapped in 11 dimensions, spiraling upward, or inward, towards something you can't name. And maybe you're not moving at all. Maybe space is moving around you, flowing in a curled channel built into the fabric by vibrating strings. And what about the strings themselves? Some ideas suggest strings can wind preferentially, more often in one direction than another. Over time, this winding bias could affect matter distribution, symmetry breaking, and even vacuum energy. So once again, what looks like a big-scale problem, the lean of galaxies, might actually be rooted in the tiniest vibrations of the cosmos. You let the strings hum around you now. You can't hear them, of course, but you imagine a soft plucking in the void, like a harp buried under gravity, and you wonder, what key is the universe playing in, and does the melody have a direction? Maybe it does. Maybe it always has. Not because something pushed the universe, but because it's been tuned that way from the very first note. You're drifting again, but this time, not through foam or strings or the ripples of space-time. Now, the universe feels solid, not in the sense of matter or rock or steel, but in a more surreal way, as though space isn't continuous at all but made of something, a pattern, a structure, something almost crystalline. Tonight you tumble through a theory that most physicists keep locked in the speculative drawer, right next to time crystals and warp drives. What if space isn't smooth, but arranged like a lattice, a cosmic crystal, a galactic snowflake, a universe that isn't continuous, but discretely stacked, like the atomic scaffolding inside a diamond? This idea isn't as far-fetched as it sounds. In some fringe corners of theoretical physics, researchers have explored models where space-time is quantized, made of indivisible units like pixels on a screen, tiny Planck-scale blocks or nodes that make up the grid we mistake for smooth space. But if that grid exists, if there's a lattice structure to the vacuum, then the implications are huge. Because lattices have direction. You know this from materials science. Crystals have anisotropic properties. They conduct heat or electricity better along certain axes. They fracture in preferred directions. Their behavior is defined by their geometry. Now imagine that geometry baked into the cosmos itself, an invisible crystal, vast beyond imagining, with a preferred orientation coded into its very structure. You float now, not through emptiness, but through this hypothetical scaffold, an unseeable grid that gives shape to space itself, and suddenly, everything feels directional. In this view, particles don't just move through space, they hop from one node to another, constrained by the lattice beneath, and depending on how that lattice is oriented, some directions might be easier, more natural, more probable, which means galaxies might spin more in one direction, photons might stretch or polarize more easily one way than another. Even gravity might behave differently depending on which edge of the cosmic crystal you're aligned with. Historians still argue whether these kinds of discrete spacetime models make physical sense, or whether they're just mathematical curiosities. But they keep popping up, especially in attempts to unify quantum mechanics with general relativity. Because smooth space-time, it doesn't play nice with the granularity of quantum fields. Something has to give. One of the more developed versions of this idea is loop quantum gravity, which we touched on earlier. In it, space is built from tiny discrete loops, interconnected in a spin network, like a spiderweb made of math. The result? A universe that, at the smaller scales, behaves more like a network than a smooth continuum. Other ideas propose causal set theory, where space-time is a series of discrete events, connected by cause and effect, more like a graph than a map. In both cases, the smooth illusion of directionless space breaks down at fine resolution, and if the graph is biased, if the network favours certain paths over others, then directionality isn't just possible, it's inevitable. You slowly spin inside the crystal now, trying to see it. It's invisible, of course, too small, too abstract. But in your mind, it looks like a diamond stretching across the sky, a lattice of possibilities, a frozen snowflake of causality, and it might just have symmetry axes. One of the more whimsical names tossed around in this area is the universe crystal hypothesis. It's mostly theoretical, deeply speculative, and yet it ticks the boxes of our sleep science rules. It's weird, it's elegant, and it introduces, once again, a preferred direction. Let's get weirder. Some quantum gravity researchers believe that the symmetry breaking that gave rise to our universe's laws may have happened along one axis of such a crystal, that the Higgs field, responsible for giving particles mass, may have condensed anisotropically, favouring certain directions in the early universe. The result? Everything from particle interactions to galaxy spins might be reflecting that long-forgotten alignment. You remember those frozen lakes with trapped air bubbles all lined up under the ice? That's what this could be. The whole universe, a frozen moment from early symmetry breaking, its invisible lattice still echoing through time. Even more poetic, some scientists suggest that the vacuum could behave like a topological insulator, a material that conducts differently along its surface versus its interior. If the vacuum of space has such properties, it might allow different kinds of wave propagation depending on orientation, and you guessed it, that's directional. Quirky historical comparison. In medieval Islamic architecture, craftsmen used repeating geometric tile patterns to represent the infinite, quasi-crystals of meaning that had no beginning or end, but subtle internal symmetry. Some of those patterns, discovered only with human artistry, were later found to obey complex mathematical rules that mirror modern ideas of symmetry and tiling in higher dimensions. Maybe the universe is tiled the same way. Beautiful, repeating, asymmetrical in ways you don't expect until you step far enough back, or zoom in impossibly close. And now you realise something else. If space is a lattice, it wouldn't just affect motion, it would affect time, because time too would be quantized. Events would occur in discrete steps. Moments wouldn't flow like water, they'd tick like a cosmic metronome. And depending on how the lattice is built, some directions might tick faster, some might stretch. It's almost comforting in a strange way, like discovering the creaky floorboards in a room you thought was floating. You thought you were weightless. But maybe you've been standing on structure this whole time, and maybe that structure is tilted. So now, when you think of all the strange alignments we've seen, spiral galaxies favouring one spin, dark flow pulling in a direction with no name, CMB hot and cold patches pointing toward the same suspicious patch of sky, you wonder, what if they're all fractures in the same crystal? What if the cosmos cracked slightly when it cooled? And now everything leans. You reach out and tap the invisible lattice once. It sings. Just once. A soft note you can't hear, but you can feel. And it vibrates through you in a single crystalline direction. That's the hum of structure. the hint of a universal axis, not pushed, not placed, just inherent. And whether we call it a spin, a tilt, an arrow, or an axis, maybe what we're really seeing is just the glint of the crystal we've been inside all along. You drift now through the silent echoes of that cosmic lattice, its shimmering structure fading behind your mind's eye. The universe still feels deliberate, patterned. But as you coast onward, another mystery rises to meet you. Less about what exists and more about what's missing. Tonight you're gazing into one of the biggest cosmic absences of all, antimatter. And if you're asking what this has to do with a hidden direction in the universe, well, stick around. Because this isn't just a mystery of imbalance. It might be a fingerprint of a directional bias embedded deep in the earlier seconds of time. Let's start with the basics. When the universe was born in the Big Bang, it should have created equal parts matter and antimatter. That's what the math says. That's what the symmetry says. For every proton, there should have been an antiproton. For every electron, a positron. A perfect mirrored dance of particles popping into existence with equal and opposite counterparts. And yet, here you are, made of matter. You're not made of antimatter. Your planet isn't. Your cat isn't. And unless there's an antimatter version of you floating through space, sipping backwards coffee, then it seems like something tipped the scales. That tipping? It has a name, baryon symmetry. It's one of the most significant unexplained features of our universe, and it may just point to a preferred direction hiding at the root of it all. See, in physics, most fundamental processes are symmetric. That is, they behave the same if you flip them, reverse them, or run them backward in time. This beautiful idea is called CPT symmetry, short for charge, parity, and time. Change a particle to its antiparticle, charge, mirror its spatial coordinates, parity, and run it backwards, time, and the laws of physics shouldn't care. But in the real universe, something breaks that symmetry. Some processes seem to prefer one direction, not just in charge, but in space and time. You float now through a metaphorical test chamber, watching a particle decay. It chooses a certain direction to spin. Now you reverse it, mirror it, change the charge, and run it backwards. If CPT held perfectly, the result should look exactly the same. But it doesn't. Welcome to the strange world of CP violation, discovered in 1964 with experiments on kaons, those delightful little subatomic oddballs. CP violation showed us that some particles prefer to decay in a specific spatial direction. Not just in a statistical sense, but consistently. It's as if nature, when forced to choose, always slightly leans to one side, and that lean is exactly what could have allowed matter to dominate antimatter. If early particle interactions were slightly biased, if certain decays occurred more often in one orientation than another, that could have created the tiniest imbalance, a 1 in a billion preference. And over time, that was enough. Enough to erase most of the antimatter, enough to leave only the matter behind, enough to make you. So here's the question that keeps physicists up at night. Why does CP violation happen at all? What causes this subtle lean? Historians still argue whether this asymmetry comes from deep, spontaneous symmetry, breaking during cosmic inflation, or whether it's tied to undiscovered particles, such as sterile neutrinos. Some even think it's a consequence of the initial geometry of the universe, a directional skew embedded in the first quantum fluctuations. If that's true, then our very existence may be the result of a universal directional bias. And here's where it gets even wilder. Some cosmological models propose that the matter-antimatter imbalance is tied to a vector field, a field with direction, not just magnitude, that existed in the early universe. These fields, if they existed, would naturally favour certain directions for particle interactions. That's not just theory. That's geometry affecting physics. Even today, scientists search for signs of directional CP violation, in high-energy experiments. Projects like the Large Hadron Collider, LHC, and neutrino observatories are hunting for anisotropic patterns in particle behaviour. If they find them, it might confirm that the universe is fundamentally tilted, not in metaphor but in the laws of its very operation. Now let's take a breath and step back. You're floating again, in a universe made almost entirely of matter, and yet the laws that govern its existence suggest there should be antimatter out there, somewhere, maybe entire anti-galaxies hidden from us by vast distances and mutual annihilation zones. It sounds like science fiction, but it's not impossible. Some telescopes are even looking for high-energy gamma rays that would signal matter-antimatter collisions on intergalactic scales. But so far, silence, as if matter really did win, as if the universe isn't balanced after all, but biased, directional. And that bias goes beyond charge, it extends into space. Quirky historical thought? In the early 20th century, Paul Dirac predicted antimatter purely through equations. He didn't think it was real, but the math said otherwise, and soon enough positrons were discovered. The universe had its mirror. But mirrors, as you know, are not perfect. What if the imbalance between matter and antimatter isn't just a mystery of decay rates, but a map? What if the lean toward matter points in a specific cosmic direction? What if the asymmetry, the reason you exist instead of annihilating into a puff of gamma radiation, isn't just a fluke, but a compass needle, a trace of an ancient push, long since cooled, that favoured this way? And so, as you float now through a universe that really should have vanished in a burst of balanced nothing, you start to see it again. That pattern, that tilt, that unspoken vector, first galaxies spinning, then dark flow, then the cold spot, then time itself, and now, you. Because if matter only exists because of a directional preference in the early universe, then so do you. You are the echo of a biased decay, a survivor of asymmetry, and maybe, if you listen closely enough, the leftover whisper of annihilated antimatter still points back toward the place where symmetry broke, where the scale tipped, where the universe first leaned. You're still floating, caught in the quiet afterglow of the great cosmic imbalance. Matter triumphed, antimatter vanished, and somewhere in that asymmetry, the universe may have revealed a preference, a lean, a tilt, a direction that persists even now. But if that's too abstract for your sleepy mind tonight, don't worry, because now we chase something smaller, stranger, quieter than light and slipperier than reason. Tonight you drift with neutrinos. They're called ghost particles for a reason. Neutrinos are so small, so neutral, so shy of interaction, that trillions of them are passing through you every second, right now. Through your skull, your pillow, your dreams, and you don't feel a thing. But the weirdest thing about them? They might just be moving in a preferred direction too. Let's set the scene. Neutrinos are fundamental particles, like electrons or quarks, but they carry no charge and only interact via the weak nuclear force. This makes them incredibly difficult to detect. You need giant underground tanks of water or ice just to spot a few, and even then, it's like watching shadows pass behind a curtain that's already pitch black. But here's where it gets interesting. Neutrinos oscillate. That means they change identity mid-flight, flipping between three known flavors: electron, muon, and tau. It's like someone juggling hats while sprinting across the cosmos. This weird behavior implies that neutrinos have mass, something we didn't even realize until the late 1990s. And the moment mass enters the chat, so does direction. Because mass affects motion, mass introduces inertia, mass can carry a bias. In recent years, researchers have begun to wonder, what if neutrinos, these elusive, almost alien particles, are subtly drifting? Not randomly, not evenly, but statistically, directionally. Some experimental data hints at the possibility that neutrinos could be violating Lorentz invariance, the principle that the laws of physics are the same in all directions and all speeds. If that's true, it would mean there's a preferred frame of reference, and perhaps even a preferred direction of neutrino motion embedded in the structure of space-time. You float now in a soup of these particles. You can't see them, you can't feel them, but you imagine them flowing like wind through a forest, brushing against you gently, all moving ever so slightly east, or up, or towards some cosmic axis we haven't charted yet. Now imagine if neutrinos behave just a little differently depending on which way they travelled. Faster this way, slower that way, more likely to oscillate on one axis than another, and imagine this happened everywhere, at every point in the universe. That's not noise, that's a compass. Some scientists have proposed that neutrinos could interact with a cosmic field, a directional background that biases their behaviour. And if this field exists, it might also explain the matter-antimatter imbalance we just explored. Because if neutrinos tilt one way, maybe the whole universe did too. Historians still argue whether such neutrino drift is real or merely a ghost in the machine, an artifact of our imperfect detectors or statistical flukes masquerading as physics. But the whisper keeps coming up. The data is messy, but persistent, like a breeze just strong enough to notice if you stop and sit with it.
And then there's the cosmic neutrino background, the neutrino equivalent of the cosmic microwave background. These are the leftover neutrinos from the Big Bang itself. They're older than stars, colder than the CMB, and still out there, still moving. In principle, this ancient neutrino fog might carry directional memory, a fossil flow, frozen in time, from when the universe was less than a second old. If we could ever detect and map it, we might see an overall drift, a vector frozen into the early universe that remains today as a subtle nudge on modern particles. Imagine that. A memory of cosmic birth, carried not in heat or gravity, but in the faint bias of invisible particles slipping through the cosmos. Want a quirky comparison? In the 19th century, explorers noticed that migratory birds often fly in slightly curved paths. They later realized birds can sense magnetic fields, using them to navigate. Now imagine that neutrinos are sensing something too, a space-time field with orientation. But instead of flying south for winter, they're slipping sideways through physics. Some physicists suggest that a neutrino wind might even affect other particles. If the neutrino background flows slightly more one way than another, it might bias decays, influence CP violation, or distort spacetime itself in subtle, cumulative ways. You're drifting through that wind now. Billions of neutrinos flow past you each second, like transparent rain. You imagine you can feel the faintest tug, not pressure, not heat, but the suggestion of a push. The kind of nudge you only feel in hindsight, when you realize you've ended up far from where you thought you were going. And if you float long enough, maybe the direction of that push starts to line up. With the cold spot, with the galaxy spins, with the dark flow, with the axis, with everything. That's the unsettling part, the cumulative directionality. These aren't unrelated anomalies. They may be symptoms of a universe that has a built-in lean, revealed through different messengers, light, gravity, matter, motion, and now, neutrinos. In that case, neutrinos aren't just particles, they're scouts. They drift in a way that other particles can't. They sneak between stars, unbent by electromagnetic fields, unblocked by matter. And in doing so, they may be tracing the hidden contour of the cosmos itself. Here's one more unsettling twist. If we ever find sterile neutrinos, hypothetical particles even more ghostly than the ones we know, they could carry no interaction with known forces except gravity. They'd be perfect probes of cosmic bias. If they exist, and some data from reactor experiments and dark matter searches suggest they might, they could hold the final clue to the universe's directional secret. But for now, you just lie there, suspended, still, while billions of invisible travelers pass through you, all whispering the same secret path. You wonder if, when you were born, The direction they were drifting was already written into your atoms. You wonder if you've always been leaning that way, just a little. You wonder if the universe ever really let go of its first spin. You're drifting through the neutrino wind still, now aware of the countless invisible whispers that pass through you every moment. But tonight, you return to something you saw before, something you couldn't stop thinking about. A spiral, or more precisely, a galaxy spinning. You've seen them, glorious, flat whirlpools of stars, gas, and dust, turning in elegant arms across the void. Spiral galaxies make up about 70% of the observable universe's galaxies, and they do what spirals do best: spin. But if you're really paying attention, as scientists have been, you'll start to notice a strange pattern, a twist in the twist. Because in some regions of the sky, more galaxies spin one way than the other. Let's say that again, slowly. If the universe were truly isotropic, equal in all directions, you'd expect to see a roughly 50-50 split between clockwise and counterclockwise spirals, depending on your orientation. Left-handed, right-handed, pure coin flips on a cosmic scale. But that's not what we're seeing. In recent years, surveys of hundreds of thousands of spiral galaxies have revealed a statistically significant bias in rotation direction. Some areas of the sky show a greater number of right-handed spirals. Others show more left-handed ones. And most disturbingly, these imbalances aren't random. They seem to align across vast stretches of space, like there's a subtle torque embedded in the cosmos. One large-scale study using Sloan Digital Sky Survey, SDSS, data analyzed over 200,000 galaxies. The results? A cosmic dipole in galaxy spin, a directional imbalance. One side of the sky had more left-twisting galaxies, the opposite side had more right-twisting ones. And yes, that's an actual observation, not just a quirky anecdote. A measurable, statistically suspicious lean. You pause in the space between galaxies, picturing these majestic spirals spinning in one dominant way, like dancers all pivoting with the same foot forward. And you wonder, who taught the universe to lead? Skeptics, of course, jumped in. Maybe it's bias in image analysis. Maybe humans, when asked to classify spirals, subconsciously prefer one direction over the other. Maybe telescopes, surveys, or software algorithms are skewed. But machine learning models trained to avoid those biases still found the same asymmetry. Historians still argue whether this pattern is a sign of something real or just a deeply buried mistake in the data. But here's what makes it even stranger. The axis of maximum asymmetry in galaxy spin aligns suspiciously well with the CMB anomalies you floated through earlier. Yes, that axis of evil. If that's true, if spiral galaxies and the oldest light in the universe are both leaning in the same direction, then something is going very, very wrong with our standard model of cosmology. You imagine the whole universe, not as a random scattering of matter, but as a slow, coordinated twirl, like a vast ballet choreographed across time and space, every galaxy a dancer, spinning to the same music. And it makes you ask a dangerous question. Did the universe have an initial spin? It's not a new idea. Some early cosmological models, long abandoned, tried to describe the universe as rotating, a cosmic angular momentum applied at birth. But the math didn't quite work. Observations didn't match. The idea was shelved. And yet, here it is again, rising from the data. Maybe the universe didn't spin like a top, but maybe its matter did. Or maybe it was spun by something else. A brain collision, a tilted inflation field, a vector imprinted in those first trillionths of a second. Whatever it was, it left something behind. A direction, not absolute, but detectable, embedded in the curl of galaxies billions of light years apart. You float now, tracing a spiral arm with your hand. You imagine its stars, born in dust, flung outward as the whole galaxy turns. Over millions of years, the spin defines its shape, its gravity, its fate. And it's not just shape. Handedness matters in physics. The universe distinguishes between left and right. Neutrinos are left-handed, DNA coils right-handed. Weak nuclear forces violate parity, favoring one spin over the mirror image. So maybe spiral galaxies are just echoing the same asymmetry, a handed universe, not just in biology or particle physics, but in structure itself. Here's a quirky callback for you. Remember that ancient belief in the music of the spheres? That the heavens moved in divine harmony? Maybe it wasn't music exactly. Maybe it was rotation. A preferred spin passed down from the first swirl of matter, still vibrating through the arms of galaxies like a rhythm you can't quite hear. And maybe you've been dancing to it all along. Now let's add one more piece to this cosmic jigsaw. Some studies have found that quasar polarizations, the way light is aligned from these ancient galactic cores, also show large-scale alignments. In some regions, quasars billions of light years apart have polarization angles that align as if responding to a shared field or direction. That's yet another layer of the spiral story. Not just how galaxies rotate, but how their light itself lines up across space. That's not random. That's structure. That's choreography. And again, the alignments? They appear to trace a direction suspiciously similar to the ones we've already seen. The dipoles, the cold spot, the dark flow, the axis, the twist in the CMB. At some point, you stop calling it coincidence. You now float, surrounded by spinning galaxies, each one like a cosmic pinwheel caught in a wind you can't feel, but might finally be starting to notice. And you wonder, if enough galaxies lean the same way, if their spins aren't random after all, if even light prefers to line up along an ancient axis, then maybe directionality isn't an illusion. Maybe it's the rule we didn't know we were breaking, and maybe, just maybe, somewhere out there, there's a point, a real one, a place all this spin and structure began, a center not in space but in the geometry of the beginning. So you float quietly, watching the spin, listening for the rhythm, feeling the turn. The universe doesn't push, it pulls softly, in a spiral. You're surrounded now by the soft, endless spirals of galaxies, those grand cosmic signatures scribbled across the dark. They keep spinning, tugging your thoughts back to the beginning, not just of the universe, but of ideas. Of how humans have tried to explain the cosmos before we had telescopes, particle colliders, or cold data maps. Tonight, you glide backward, not through space, but through time, toward the minds that first tried to make sense of direction in the universe. And as you'll soon discover, this isn't just a modern obsession. We've been looking for a cosmic up for thousands of years. You start with Aristotle, 4th century BCE. He imagined a universe where everything had its natural place. Earth at the center, then water, air, fire, and finally the heavens. A layered onion of perfection. The celestial spheres rotated in perfect harmony, and the cosmos itself had a kind of vertical hierarchy. Up was divine. Down was earthly. Direction wasn't just spatial, it was moral. Then came Ptolemy, who built on this with epicycles. Nested circles meant to explain planetary motion while preserving the idea of a geocentric, symmetrical cosmos. Still no hint of randomness. Still all structure, all direction. But the real break, one that shattered the idea of any cosmic favoritism, came with Copernicus in the 16th century. You remember the story. He demoted Earth from its divine pedestal and placed the sun at the center instead. Suddenly, up and down lost meaning. There was no privileged spot in the universe, or so we thought. Fast forward to Galileo, who pointed his telescope upward and realized Jupiter had moons, and they orbited not Earth, but Jupiter. The idea of cosmic directionality took another blow. The heavens were not perfect. They were dynamic, chaotic, turning without a divine compass. And yet, even in this expanding model of the solar system, humans kept hunting for structure, for alignment, orientation. Then came Isaac Newton. Gravity connected everything but space itself. That was a stage, an empty, unchanging grid where the laws of motion played out. There was no preferred direction, no spin to space, just force and motion. But Newton couldn't explain one odd thing, the way things moved relative to each other. There was no true answer to which way is the universe facing. Then came Einstein, and everything changed again. In 1915, with general relativity, Einstein told us that space and time were not separate, rigid containers, but one, flexible, dynamic entity, space-time, and it could bend, twist, even rotate. Yes, rotate. Though we often imagine the universe as expanding in all directions equally, some of Einstein's solutions to his field equations allowed for global rotation, a universe spinning like a basketball on a finger. This idea was explored further by physicist Kurt Gödel, yes, that Gödel, in 1949. He developed a solution to Einstein's equations that described a rotating universe where time itself was curved so extremely you could travel in circles and return to your own past. Of course, that idea was too strange to be taken seriously by most physicists. A rotating universe would leave observable effects, like directional biases in cosmic radiation. At the time, we hadn't detected any. But now, maybe we have. Because remember that CMB alignment, the cold spot, the axis of evil? All of them could be reinterpreted as faint signs of a global spin, a Gödelian whisper in the dark. Historians still argue whether Gödel's universe is physically viable, but his model remains a haunting reminder that the equations themselves allow for directionality, even if we don't want them to. And here's another curious twist. Early cosmological models also tried to preserve homogeneity and isotropy because they reflected Enlightenment ideals, fairness, symmetry, universality. A directional universe felt politically uncomfortable. It suggested inequality, a cosmos that chose favorites. But the data, as you've seen, keeps betraying that hope. You drift further forward into the 20th century when the Big Bang theory became dominant. It told a cleaner story. The universe began as a hot, dense point and expanded uniformly. No center, no edge, no preferred direction. Just pure, impartial explosion. But even the Big Bang model assumes something crucial: cosmological isotropy. The idea that, on large scales, the universe is the same everywhere and every direction. The problem? That's an assumption, not a proof. And more recent observations, galaxy spins, quasar alignments, the dark flow, all call that assumption into question. So now, as you hover between theories and centuries, you start to see a pattern, not just in the sky, but in our ideas. Over and over, we've tried to erase directionality from the universe, to make it smooth, fair, symmetrical, but nature keeps leaving crumbs, hints, leanings. Maybe we've misunderstood something fundamental. Maybe the idea of a directionless universe is just another human invention, like thinking the Earth is flat because the hills nearby look straight. And maybe the real truth has been quietly spinning in front of us all along. Want a quirky historical parallel? In Norse mythology, the universe was held together by Yggdrasil, the world tree, its branches connecting different realms in a clear, vertical order. Heaven above, hell below, Midgard in the middle. It was a deeply directional cosmology, where you were mattered. Modern cosmology discarded that tree. But maybe the roots still reach through the stars. You drift now, letting time collapse around you. Aristotle, Einstein, Gödel, they all asked the same thing. Does the universe know which way is which? And now, with data at our fingertips, the question returns, not as myth, but as math. Maybe the center isn't a point. Maybe it's an axis. Maybe it always was. And you've been facing it without knowing. You're spinning now. Not wildly, not even visibly, but you can feel it in your chest. A slow, patient turn, like a weather vane responding to something almost too subtle to notice. Like you've finally lined up with something. Something that may or may not exist. Something called the cosmic axis. The closer you lean into it, the harder it is to ignore. And you're not the only one. Tonight, you stand with modern scientists at the edge of certainty, looking straight down the barrel of controversy. Because despite everything, the CMB cold spot, the spiral spin patterns, the quasar alignments, the neutrino drifts, there are still experts who insist this so-called axis is just an illusion. The debate is alive and it's growing louder. Some say the axis is a cosmic signal, Others say it's human error, no more meaningful than a shadow on a smudged lens. But whichever side you're on, the same uncomfortable truth remains. There's something out there we didn't expect. The axis goes by many names in the literature. The axis of evil, sure, that dramatic clickbait label, but also cosmic dipole alignment, quadrupole-octopole correlation, or simply large-scale statistical anisotropy, different terms for the same disobedient whisper. And here's the thing, it keeps showing up. It's not just the Planck satellite, or WMAP, or the Sloan Digital Sky Survey. It's across multiple independent data sets, observed using different methods and instruments, separated by time, location, and intention. And yet they all seem to point in roughly the same direction. But skeptics have a solid argument. Of course you see patterns, they say. You're looking for them. That's what humans do. We're meaning-making machines, after all. We spot faces in toast, animals in clouds. We turn a random dip in data into an axis and call it mysterious. Is this cosmic alignment just pareidolia with photons? Maybe. Historians still argue whether the persistence of the axis across multiple experiments is truly significant, or whether we've just underestimated our own noise. It's hard to separate the signal from the static when the static is built into your method. Let's talk about one of the biggest suspects, foreground contamination. To detect the cosmic microwave background, satellites have to filter out local emissions from our galaxy, our solar system, even the instruments themselves. And it turns out, our Milky Way sits directly in line with the axis of evil. Coincidence? Maybe. Or maybe the axis is just residual radiation from the galactic plane, poorly subtracted from the CMB data. If that's true, then the entire thing collapses into a pile of spreadsheet dust. But here's the pushback. Researchers have applied different foreground removal techniques over and over. Some even mask out the galactic plane entirely, and still the alignment holds. Weaker, sure, but present. The data doesn't scream, it just refuses to vanish. You float above this disagreement like a satellite, observing the scientific tug-of-war below. One side clings to Occam's razor, simpler explanations, fewer assumptions. The other side points at the evidence and says, how many coincidences do we accept before we call it a pattern? It's more than just a technical argument, it's a philosophical one. Do we demand that the universe be symmetrical because we want it to be? Or do we listen to the subtle hum that says, I am not what you assumed? Here's a telling fact. Many cosmologists accept the anomalies as real, but not yet significant. The statistics are intriguing, but fall just short of what physicists consider a discovery. That magic number is 5 sigma, less than a 1 in a million chance of being random. Most of the CMB alignments hover around 3 to 3.5 sigma. That's not nothing. It's compelling. But it's not conclusive. It leaves us in a liminal space, too odd to ignore, too noisy to embrace. Want a quirky analogy? Imagine walking into a room and every chair is facing one wall. You ask why. People shrug. Random chance, they say. But then you walk into another room, same pattern, then another. At what point do you stop and ask, what's on that wall? That's the cosmic axis, not proof, but suspicion. Some researchers have even begun designing future experiments specifically to test the axis. Next-generation CMB satellites, galaxy polarization surveys, and ultra-high-resolution radio maps. They're all asking the same question. Is this real? Because if it is, the implications are massive. A real cosmic axis would mean the universe is not isotropic on the largest scales. That would shake the foundations of cosmology, models, predictions, interpretations. The whole standard model of the universe would need to be revised, possibly replaced. We'd be forced to accept that the universe has a preferred direction. Not because of local structures, not because of human bias, but because that's just how space is. You begin to imagine that direction now. It's not a compass bearing, not a line on a map. It's something more primal, a thread through space-time, connecting distant anomalies into a single filament of meaning. And that raises a darker possibility. What if we're inside a larger structure we can't perceive? A supervoid? A warped region of space-time? A bubble universe with asymmetrical inflation? Or even stranger, what if this direction is a boundary condition of the universe itself? A remnant of how our universe was spawned in the multiverse? Our own Big Bang slanted by the geometry of the higher dimensional space it emerged from? Of course, these are just hypotheses. Some elegant, some untestable, some outright unhinged, but they all share one thing: they point. Because deep down, we're all looking for where things point. Not just galaxies, but meaning, place, orientation, that sense that the universe has a spine and we are vertebrates trying to stand upright against it. You drift in that question now, not lost, not found, just curious. You've seen the evidence: the galaxy spins, the cold spot, the dipole, the dark flow, the neutrinos, the lattice, the string, and now, the axis. Maybe it's real, maybe it's not, but it won't go away. And that, perhaps, is the loudest signal of all. You float there, caught between possibilities, suspended like a dust mote in the flashlight beam of a very confused cosmos. You've seen enough strange alignments, unlikely patterns, and directional whispers to question everything. But now comes a deeper, more existential twist. Because what if all these hints, the spin preferences, the alignments, the cold spot, the strange axis, aren't signs of a lopsided universe at all? What if they're signs that you're inside a simulation? Yes. Tonight you tumble, softly, sleepily, into the ultimate fringe hypothesis, the simulation hypothesis. If you've ever played a video game, you already understand the basic idea: a system governed by rules, coded by an external intelligence, populated with simulated entities. Some theoretical physicists, philosophers, and even a few computer scientists propose that our universe could be just such a system. And if that's true, then everything you've seen, every strange directionality, might not be part of a flawed cosmological model, but part of the program. In other words, the universe doesn't have a preferred direction because of physics. It has one because it was coded that way. Let's take a slow, sleepy dive into what that means. First, the logic. The simulation hypothesis, in its most formal expression, is often linked to philosopher Nick Bostrom, who argued that if advanced civilizations can create hyper-realistic simulations, and if they want to, then statistically, it's more likely we're in a simulation than in the base reality. A bit unsettling, yes, but not entirely implausible. And if we are in a simulation, it might explain why the universe appears to have structure. Programs are efficient. Simulations often optimize data rendering. In a massive system, it would make sense to encode shortcuts or coordinate biases to conserve resources. Imagine a video game world with infinite terrain. Do you really simulate every blade of grass? No, you generate detail dynamically, often based on player position or camera angle. And the deeper you go, the more things get simplified. Now ask yourself, what if the cosmic axis is a rendering bias, not a physical feature of the universe, but a directional artifact of the system we're in? Some speculative physicists have proposed that if we lived in a digital cosmos, we might detect anisotropies, subtle irregularities in physical constants, particle behavior, or background radiation that correspond not to physics, but to program architecture. A preferred axis? That might just be a grid alignment, like a vertical seam in a digital skybox, or a programming coordinate system that, for simplicity, leans in one global direction. And what about that cold spot? Some theorists suggest it could be a glitch, or maybe a debug artifact. Imagine the developers needed a test zone, a sandbox. Maybe the cold spot is just a marker left by cosmic engineers. Historians still argue whether any of this is testable, and that's the real challenge. Unlike traditional physics, the simulation hypothesis isn't easily falsifiable. If the system is sophisticated enough, it would be indistinguishable from a real universe, unless it leaks. Unless the creators weren't quite perfect. Unless we start finding subtle, unnatural patterns. Like, say, galaxies that all spin the same way, or radiation fields that point in an arbitrary direction, or preferred axes that break symmetry for no clear physical reason. You begin to think differently about the anomalies now, not as contradictions, but as breadcrumbs, leftover instructions, design quirks, maybe even a signature. And you wouldn't be the first. In the 2000s, some researchers at Fermilab and MIT suggested that if space-time is actually a lattice, digital, discrete, at the smallest scales, we might find evidence of it in cosmic ray propagation. High-energy particles moving through the universe might scatter or bend slightly if space isn't smooth, but quantized. We haven't seen that yet, but the search continues. More fringe yet are those who claim to find code-like structures in nature, binary patterns in physics, mathematical recursion in cosmological constants. Some even point to error correction codes found in string theory equations, actual digital constructs, they claim, hidden in the math. To be clear, the mainstream physics community treats these claims with extreme caution, but they exist. And the idea that our universe might be computed rather than emergent is gaining slow, cautious attention. Let's not forget, in many ancient cosmologies, the universe was imagined as spoken, written, or sung into being. In some creation myths, the gods used symbols, names, or even literal code to call reality into form. Quirky callback? The Greek philosopher Pythagoras believed that numbers didn't just describe the universe, they were the universe. That all things were expressions of mathematical harmony. A simulation, you might say, without the GPUs. You pause now, floating in the black code space of possibility. You imagine the stars above as pixels, the galaxies as subroutines, the cold spot as a rendering bug that no one bothered to patch, and the cosmic axis, just a Zaxis default orientation on the great modeling software of the stars. And yet, it all still feels real. The weight of galaxies, the noise in the CMB, the particles that pass through you without permission, whether this is base reality or a cosmic Minecraft server, you are still inside it. And the direction? It's still there. So the question becomes, is it a message? Are the anomalies the result of physics or programming? Is the cosmic axis a fluke of gravity, or the alignment tag left in the universe's XML file? You drift in that ambiguity now. Comfortable, quiet. Because even if we're in a simulation, the rules still matter. The spin still happens. The galaxies still turn. Whether you're a line of code or a cloud of atoms, the cosmos still hums with a direction it refuses to explain. Maybe you're not meant to understand it. Maybe you're just meant to feel it. So you close your eyes, and in the distance, something aligns. Not because it has to, but because it was told to. You've followed the trail all the way here, through radiation and spin, through theoretical twists and ancient myths, through gravity, neutrinos, lattice structures, and possibly even code. You've leaned into the idea that the universe, in all its vastness, might not be as directionless as we once thought. And now, for the final step, you cross into the deepest question of all. If there is a hidden direction, what does it mean? Not just scientifically, but cosmically, personally. You're not just a passive observer anymore. You're part of this. You've always been. Atoms from a biased Big Bang. Thoughts shaped by asymmetrical laws. A body built from matter, not antimatter, because the universe decided once upon a time to lean. So tonight, let's follow that lean. Let's assume, just for now, that the direction is real. The axis exists. It spans the cosmos like a whispering thread, woven through microwave background data, the rotation of galaxies, and the drift of ghost particles. What now? Let's start with the science. If we confirm a universal direction, a measurable, reproducible anisotropy in space-time, our entire cosmological model would need revising. The cosmological principle, which holds that the universe is homogeneous and isotropic on large scales, would collapse. And with it, many of the assumptions baked into models of inflation, dark energy, and even cosmic expansion. We'd need to rethink how the universe began and whether its early conditions included orientation, perhaps a vector field, a twisted geometry, or a rotating inflaton field during the first fractions of a second. That would shake the foundation of inflation theory and offer a new lens on the structure of everything. And then comes the bigger leap. Some theories suggest that directional asymmetries could be caused by interactions with neighboring universes, regions beyond our own cosmic bubble. In this multiverse scenario, we're one pocket in a quilt of inflating realities. If we ever bumped into another bubble universe, that collision could leave an imprint, a dent, a tilt. It's one of the proposed explanations for the cold spot, by the way. And in that case, the direction wouldn't just be an internal quirk. It would be evidence of something beyond our universe, something larger. A metastructure with its own geometry and orientation. Our hidden axis could be a bruise left by contact with the outside. Or maybe it's not a bruise at all. Maybe it's part of the structure. In Theories of Conformal Cyclic Cosmology, put forward by Roger Penrose, the universe goes through infinite cycles, each ending in a kind of thermal death, which becomes the next universe's Big Bang. In that view, what we interpret as randomness might be echoes from a previous cycle. A preferred direction? That could be a memory. A scar left over from a universe before ours, still gently tugging at the fabric. And now, you start to feel small again. But not in the cold, empty way. In the way you feel when you realize you're inside something bigger, older, stranger, and that something is moving, not just outward in expansion, but along a trajectory. You let that settle in your thoughts. The idea that the universe is going somewhere. Not metaphorically, literally. Every second that passes, every photon that travels, every spiral galaxy that twirls, it all subtly nudges in one broad direction. It's not obvious, it's not strong, but it's there. The axis isn't a line drawn in space, it's a tendency, a preference, a reminder that the cosmos is not symmetrical, not neutral, not balanced in every possible way. And neither are you. You're made of biased matter. You see light that's already redshifted. You occupy a planet that spins, orbits, leans into a galactic plane that itself may be drifting. You are directional. From your heartbeat to your brain's hemispheres, your biology reflects preferences, dominance, polarity, orientation. So maybe the axis isn't out there. Maybe it's in here too. What if consciousness itself is entangled with cosmic direction? What if the very process of observation is part of the alignment? Some researchers have speculated, quietly, nervously, that the act of measurement may be subtly affected by universal bias. That perception, time, and even thought could be shaped by deep space asymmetries we haven't even named yet. You blink at that, slowly, sleepily. Because if that's true, then the question is no longer, is there a direction? It becomes, have we always been facing it? Have our telescopes, our measurements, our dreams all leaned this way because something deep in the code of reality said, this is forward? Even in ancient mythologies, directions had meaning. East was rebirth, west was death. The zenith marked divinity, the nadir, descent. Every temple, every compass, every calendar tried to trace invisible lines through time and place. We called them sacred. Maybe they were just echoes of the same axis we see in the sky. So where does that leave you now? Drifting. Always. But with a question you didn't start with. Not what is the direction, not even where does it point, but this. What will you do with it? Because if the universe is leaning, if it's going somewhere, if it has a long, slow tilt guiding its motion, maybe you're meant to feel it. Maybe you're meant to align. Not in location, but in intention, in curiosity, in motion. After all, every galaxy is spinning, every photon is flying, every moment is unfolding along the grain of something ancient and unnamed. Maybe you've always felt that lean, in the quiet, in the dark. And now, at last, you have a name for it. Direction. You breathe in the last stillness. Let it pass through you, and turn. Just a little, toward the place the universe has always pointed. You're still now, not in space, not in time, just in stillness. The galaxies spin behind your eyes. The background radiation fades into soft static. The particles, the twists, the echoes of the cosmic axis drift away like the last notes of a song too old to remember. There's nothing left to figure out tonight. No more theories to test. No more equations to untangle. Just the feeling of direction, not as force, but as a presence. A gentle lean in the dark. And maybe that's enough. Maybe you don't need to know where it leads. Maybe the quiet knowledge that there is a path, even a subtle one, is what lets you finally let go. So let yourself exhale. Let your thoughts loosen. If you've been searching, across data, across dreams, across time, know this. The universe was never completely random. There was always a pattern, a rhythm, a grain. You've been floating along it since the moment you were born, shaped by it without knowing, and now you can just be. No need to align. You already are. So wherever you are in the world, whether it's midnight or 4 a.m., or that quiet space just before dawn, you are exactly where you're supposed to be. Rest easy now. The universe has a direction, and tonight, so do you.